Hello everyone and welcome to this tutorial on TurboMOLE and its graphical user interface TmoleX. In this video, we'll walk through the geometry optimization of a molecule using ibuprofen as an example and then calculate its vibrational frequencies to check whether the optimized structure is a true local minimum. Let's get started by launching the TmoleX application. Once it's open, click on New Project and choose a directory to save your project. I'm creating a folder named ibuprofen in my documents. This will contain all the files related to geometry optimization and vibrational frequency analysis. Next, we define the structure of the molecule in the Geometry tab. Notice the Geometry button is currently red. This means no structure has been specified yet. You can import the molecule from a file such as XYZ or mol. Click Import Coordinate File, navigate to your file and select it. You'll now see a table with atomic coordinates. Our ibuprofen structure has 33 atoms. Click Open 3D Molecule Builder to visualize it. Use your right mouse button to rotate and inspect the molecule in 3D. You can also draw the molecule manually. Click Draw 2D and use this interface to build it atom by atom. Alternatively, you can paste the smiles string for ibuprofen into this box and click Smiles to 3D. After building or importing the molecule, you can optionally do a pre-optimization using XTB. Once the geometry is defined, the Geometry tab turns green and we can continue. In the Atomic Attributes section, choose a basis set. I'll go with Def2 SVP for all atoms. Now we set the molecular attributes like charge and spin. This tab is still red because we haven't generated the molecular orbitals yet. Click on Generate MOs. You will see it generates 56 doubly occupied orbitals for our system. Then hit Continue. Now we select the method for our calculation. Let's use DFT with RI acceleration and choose the B3lib hybrid functional. Leave the rest of the settings as default and click Continue. We're ready to start the job. In the Start Job tab, select Geometry Optimization. You can adjust SCF convergence, gradient norms, and max optimization cycles here. Click Save and then Run to start the calculation locally. Once the job starts, you'll see it listed here. In the bottom left, you'll see the energy and gradient values for each step. On the bottom right, you'll get a live plot showing energy versus optimization cycle. When the job completes, go to the Job Results tab. You'll find key outputs like whether SCF and geometry optimization converged, final HOMO-LUMO gap, total energy and final gradient, convergence plots, dipole moments, and so on. You can click on the Convergence button to see the plot of energy versus optimization cycle. Clicking on the Energy button shows the energy at each time step. You can also visualize the forces or gradients at each cycle by clicking on the Gradients button. Use the slider to move through the geometry optimization frames. You can see how the forces are higher for the initial geometry and how they become smaller as the optimization progresses. It can also be used to create a movie of the optimization. You can also visualize the dipole moment of the molecule by clicking on the Dipole Moments button. The values of the dipole moment are also shown in a text window ready for copy and paste. Finally, the HOMO-LUMO gap is shown here. Now let's verify if the optimized geometry is a true minimum. To do this, start a new job with the current data and select Spectra and Excited States, and then go to IR and Vibrational Frequencies. You can compute all vibrational modes or just the lowest end frequencies. Click Save, give your job a name, and then run it. Once complete, head to the Results tab. You'll find the 0-point vibrational energy and a list of calculated modes. There should be 99 vibrational frequencies for our 33-atom system. 6 of these correspond to translation and rotation and are near zero. All remaining frequencies are positive, indicating a stable local minimum. You can view the IR spectrum by clicking on the IR spectrum button. To get the table used to generate the plot, you can click here. It is also possible to visualize the vibrational modes by clicking the Vibrations button. Select any given mode and then hit play to visualize it. It is also possible to get some thermochemical properties like entropy. And that's it! You have successfully optimized the geometry of ibuprofen and confirmed it's a stable structure using TmoleX and TurboMole. If you found this tutorial helpful, please like, share and subscribe for more tutorials on TurboMole and TmoleX. Thanks for watching and see you in the next video.